Today's lesson is on rational functions. We're going to start by looking at rational functions the same way we looked at all of the functions we've covered so far in this course. First thing we want to do is really define what a rational function is. And we will be looking at a number of rational functions, but today we're going to focus on something called the reciprocal of a linear, and we'll get to that in a moment. But a true definition of any rational function is simply a polynomial divided by a polynomial. And examples of this might be in the form y equals x minus 3 over x plus 4. Each of these are polynomials. An example that is not rational might be something like x minus 3 over x to the negative 2. And by definition, we've seen that x to the negative 2 is not a polynomial. It is something else. And if you were to simplify this, you would end up with something under the look of x minus 3 multiplied by x squared, because the reciprocal of x to the negative 2 is 1 over x squared, and that would give you a cubic equation, which we know is not irrational. So they need to take this form. So let's go ahead and take a look at a couple of them. The one that we're going to be focusing on today is the reciprocal of a linear. And it gets its name because reciprocal means that the numerator is going to be a constant, 1 in this case, and the denominator is how it gets its name, reciprocal of a linear. We will be taking a look at reciprocals of quadratics and true rational functions. So you'll notice that in this example that graphs the reciprocal of x minus 2, we now have different looking functions, different looking graphs. And the reason is because, and you learned this in grade 11, is that whenever we have a rational, you have to look at restrictions. So in this particular case, we know that x cannot be equal to positive 2. And if x can't be equal to positive 2, then you sketch a vertical asymptote at that place. And we'll talk more about asymptotes in this exercise. So let's get started. The first question is asking us to consider a reciprocal of x. So the linear piece of this is y equals x, and we're trying to find the reciprocal of it, 1 over x. So the first thing they ask us to do is state restrictions. Well, restrictions are basically anything that x cannot be. And from previous years of math, anything divided by 0 is equal to an undefined value. And so in this particular case, x cannot equal 0. Now in grade 11, you recognize that if you were asked to sketch a graph like this, you would have a vertical asymptote located at x equals 0. The next thing they ask us to do is make a table of values and sketch the graph. And this is one of the few times we'll actually be going through with this, because we will focus in on characteristics from this point forward. But it is a good idea to create a table of values. So I'm going to start with some extreme values like negative 100, negative 10, negative 1, and then I'm going to pick some values that are fairly close to 0. And I'm going to use 0, and then I'm going to use the same values but on a positive side. And when you create a table of values, you're taking each value and plugging it in. So 1 divided by negative 100 is equal to negative 0.01. And 1 divided by negative 10 is equal to negative 0.10. And you could continue this pattern. So if we were to sketch something like this, because of the large values, we're not going to be able to actually sketch negative 100 and 0.01, but we know it's on the negative side, getting very, very close to this x-axis. The first point we will sketch is at -10 and -1, somewhere right about here. The next point would be -1 and -1. And then we start getting very close to the y-axis. And the values that we see here are -1 and -10, all the way down here, very, very close. And then obviously we have another point even closer. So our sketch might look something like this, getting very close, cutting through that point, and then traveling all the way down. Continuing to sketch, we're at very close to the y-axis. We're way up at 100. We're not able to show that, but we are able to show at 1 and 10, and 1 and 1, and then way over here, 10 and 1. And we get a similar sort of looking graph appearing here. There's our sketch of y equals 1 over x. Notice what happens as it gets very close to this sort of restriction, this asymptote located at x equals 0. And then we also notice that there is a horizontal asymptote right along here at y equals 0. So it's important for us to state these. So x equals 0 is the vertical, and y equals 0 is the horizontal. We're going to talk about the characteristics now. And so if we go back to answering some other questions, it says down below here, describe what happens to the function as x approaches 0. So as x approaches 0. So let's go back to the graph and say, okay, as x approaches 0 from the left, the y values get increasingly larger negative. So let's record that. As x approaches 0 from the left, the y values, and I'm going to use this little arrow as approaches negative infinity, because it just does continue on and on forever. The next question is what happens as x approaches 0 from the right, and we would see that it's going up, 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 approaching positive infinity. And so we use that little arrow, y approaches positive infinity. Then it asks us what happens as x approaches negative infinity. So what's happening with the y values? Well, y values are approaching something. So let's take a look. So as so let's take a look at x approaching negative infinity. As x approaches negative infinity, way out here, y approaches 0 from the negative, and that's important to state. So y is approaching 0, and I'm going to write in here from the negative. So that just tells me that my function exists below. And we can also say as x approaches positive infinity, we can see that y approaches 0 once again, but this time from the positive. And let's go back to that graph and take a look. So as x approaches positive infinity, y is approaching 0, but from the positive side. It's important to point out positive or negative. So all we're going to do is now we're going to look at different reciprocal functions and pull out those same characteristics. The best way to pull out those characteristics is probably to sketch it. So that's going to be our goal. So let's look at the function g at x is equal to 1 over 2x minus 3. Once again, it's important to recognize that this is a linear, and the name of this is called reciprocal of a linear. So you identify it by what's on the bottom. So states restrictions. We can do that very quickly by looking at the domain, or the denominator, and setting it equal to 0 and solve. So when we substitute 3 over 2 in, the denominator will become 0. So our restriction is x cannot be equal to 3 over 2. Sketch the graph. Alright, so I'm going to do a quick sketch of the graph without having to do a table of values. And it's going to be a little bit rougher sketch, but that's all we want at this point, because we really want to focus in on the behavior. So the first thing I'm going to do is I'm going to plot my vertical asymptote, because I've already identified that. X cannot equal 3 over 2, so I'm just going to estimate that it's right about here. I am going to label it x equals 3 over 2, and that's important for all asymptotes. Then I want to focus in on other things, so I want to see if I can pull out things like the x and y intercept. So to find the x-intercept, what I'm going to do is I'm going to set the y value to 0. Let me just tuck this out of the way here. And to find the x-intercept, we're going to set y to be equal to 0. Here's the y value. So I have 0 is equal to 1 over 2x subtract 3. When I multiply both sides by 2x minus 3, these will cancel, but any time I multiply anything by 0, I will get 0 is equal to 1, which doesn't make a whole lot of sense. But what that tells us is that there are no x-intercepts. So if there's no variable to solve for, then there's going to be no x-intercept. When that occurs, you are also going to have a horizontal asymptote, and that asymptote is going to be located at y equals 0. The next item that we can pull out is the y-intercept, and the y-intercept is when we set x to be 0. So just cover that up, and what's left over is 1 over negative 3, and there it is. So I'm going to go and plot that right about here. And now what I can do is I can use that approach that we used in the last question, where we looked at things like, what happens as x approaches, let's go with negative infinity. So looking back at this reciprocal now, if I take a value really, really big, like a billion, then I basically have 2 billion subtract 3, but I said let's make this approaching negative, so it'll be negative 2 billion. So really what I'd have here is a very, very large number in 3. Now, I don't want to get hung up on the fact that I have to pick a number. I just want to remember that if I take a small number divided by a very large number, it's going to approach 0. And the negative sign means it's approaching 0 from the negative side. That means that there is a point somewhere about here. And I could do the same thing as x approaches positive infinity, so way out to the right. Then I would look and I would say that I have the same situation. I have 1 divided by a large number, and that always approaches 0, this time from the positive, so I have a point here. Now if we just look at the left-hand side of this graph right now, and I recognize that there is a point below and another point located at the y-intercept, then I can just use this commonality of I'm drawing my line, and as I get to this point I have a choice. I can either go straight, but then I bump into the vertical asymptote. If I go up, I hit another horizontal asymptote, and the rule is we can't pass through asymptotes. So the only option I have is to go down. And if I were to use another test point really, really close to 1.5, say 1.4, I would get a very large negative number. I can use the same principle here. As I'm traveling towards this asymptote, my choice is either to go down, but then I'd have to cross an asymptote, and that doesn't normally happen, so I have to go up. And what I end up having is these two graphs that hug these asymptotes.